Hello students, welcome to the second lecture on D and A block elements. In this lecture we are going to discuss the general characteristics of the D block element, D block transition element. In the previous lecture we have discussed that all the transition elements are D block elements, but all the D block elements is not the transition element, because you know the last three members of each series, they are not basically a transition element. We can call it a non-transition element. So heading of today's lecture, that is the general characteristics, or we can say the physical properties of the transition elements. Physical properties, that is a different type of physical properties that we have to discuss. That is not possible to discuss each and every in the same lecture. That is why we will make it a part 1. That is physical properties of transition element part 1. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. All the transition element, if you recollect, you will find the electronic configurations. Because we know the chemical properties of any element, it depends on the electronic configurations of the valence cell. Here, all the transition elements resemble in the physical and chemical properties because their outer cell electronic configurations, that is NS2, is similar, and that is why they will exhibit almost similar properties, and that is a basic thing, basic difference between the representative elements, or we can say the main block element, that is ASP element, SP block element, that we will know. The main difference that there is a lot of similarity we will observe in the rows also. In the rows, normally what happens in case of S block or P block, we will find that elements having the different type of property as we go for the left hand side of the periods to the right hand side. But here there is a similarity we will observe in the row itself, and in the group itself we also some similarity that we are going to discuss in this lecture. Before that, let us understand its general characteristics. All the transition elements are metals. They are very hard metals. So what we will find, there is a different types of properties. Number one property, that is it is having high tensile strength. High tensile strength. Second thing, that it is having high melting point and boiling point. High melting point and boiling point. Third thing, it is having, because it is a metal, so it will having this property, ductility. Then it is having property of malleability. Then it is having the property of the good conductor. Good conductor of electricity and heat. 6th point, it is having a metallic structure. That we know the precious element that we know as on that is the platinum, gold or silver, all having a good metallic structures. That is why they are metallic luster. And 7 point, that it forms alloys. So these are the 7 very general properties that we observe in case of transition metal element. And this property you may not find in the last member of this group of this series, that is the zinc, cadmium and Ag. So these are the general characteristics, but we are not going to discuss the very important other general characteristics, that is the physical properties. That first we are going to discuss the atomic radius. So first we will discuss the atomic radius. In this case, what we will discuss, how atomic radius has been, there is a trend. What is the trend of the atomic radius, that we are going to discuss. As we go across the series, what we find that there is a continuous decrease in the atomic radius, and it is up to the middle of the series that we will always understand in terms of graphical representation. Let us have some statement on this point. So at the middle you will find there is a minimum radius. After that you will not find much of a difference. The radius become almost constant, and at the end you will find there is a slight increase. And this trend is observed all the 3 series, that is 3D series, 4D series or 5D series. Every series you will find the same type of observations, but there is some notable points, significant points that we will discuss regarding the 4D and 5D and 3D if we compare with their atomic radius. What we find, there is 4D and 5D have the radius, higher radius than the 3D. So we can say that as we go down the groove, we will find the atomic radius goes on increasing, and that is why it is so, because there is a incorporation of one new cell. Because in the 3D there is a last cell, that is the outside cell, 4S cell has been incorporated. In the 5D you will 4D, that is you will say that is the 5S. In the 5D that is the 6S. So every time you will find there is a incorporation of a new cell, and that is going to increase the diameter of this atom as we go down the groove. So when we go across the groove, it is the diameter decreases, the radius decreases with the increase of the atomic number, and after some time it is become fixed, and at the end you will find there is an increase in the radius. So this statement can be understood with the help of this graph also. We discuss the atomic radius in terms of the graphical representation of all the 3 series. This is, we are taking the atomic radius, then it is, this is atomic number, and this is atomic radius. Now if we go from the first series, what we find, that is the titanium, then here this is a titanium, suppose titanium, then where this is a vanadium and chromium. This is chromium, and after that we will find this is not much of this. So this is, you can see this is copper or zinc, what this is zinc, suppose this is zinc, and here this titanium, this is vanadium, then you will see this is the graph. As we move from the left hand side of this to right hand side, you will find there is a first there is a decrease in the atomic radius, afterwards that will be increase. This is for the 3D transition element. Now 4D, that you will find and 5D so this is the 4D and this is the 5D. So what we will find from this diagram, that as we go, as the atomic number is increasing, the radius goes on decreasing, and at the middle of the series, this is a chromium, suppose this is chromium here, middle of the series, that is we know molybdenum, and this is a tungsten. What we will find, that is a maximum decrease, and after that there is no such increase or decrease, no change, there is a constant, and at the end there is a increase. But what we understand from this graph, that is the 4D and 5D, if we compare their atomic radius, it is much more higher than this 3D that we already discussed due to the incorporation of cell. But if we compare between the 4D and 5D, what we will find? We will find that the gap is very less. Gap is very less means that diameter is almost same. Let us understand first why it is so that when the atomic number goes on increasing, while the radius is decreasing. This is due to this fact, as the atomic number increasing means we are increasing the proton in the nucleus, so the nuclear charges has been increasing, and that is going to increase the attractive forces on the outside cell, and there is a sinking of the outside cell, and you can find that atomic radius is being responding in this way. So that's nuclear charge is increasing, the attractive force is increasing, that is why this you observe. But at the middle of the series, there is a higher number of d electrons. You can see in the chromium how much d electrons there? There is 5 d electrons. D electrons you will see 5 d electrons. Here molybdenum also 5, and it's a tungsten, it is also 4. So there is a maximum number of d electrons, and after that this d electron goes on increasing, and d electron will increase the screening effect at the atomic radius AR. It is a function of, we can say the atomic radius is the function of the atomic number. So as the atomic number is increasing, the atomic radius is decreasing up to the middle of the series, and after that it is become fixed, and at the end it is again increasing. And what is because? This is due to the first case, that is the nuclear charge. The main thing, the nuclear charge is increasing. Nuclear charge influence this decrease in the atomic radius, and we will find after that the screening effect of the d electrons. Then comes the screening effect. Of d electrons. It is much more than these attractive forces arises from the nuclear charge. So it will much greater, scattering effect of d electron is much greater than this nuclear charge. That is why there is the diameter is more or less same after the middle. And afterwards at the end, so there are three things is there. Nuclear charge decreases at up to middle, you can write up to middle of the series. Then that is not going to decrease the diameter further, because this due to this scattering effect, the outside electron will not face the effective nuclear charges so much, so that will become constant. It will make the diameter constant. And after that, at the end, what we find, that is the repulsive force between the electrons. Repulsive force between the d electrons. Because d electrons has been putting in the same cell, that is why there is a lot of repulsive force, and this will increase the electron crowd. This will increase the outside cell electron crowd, and this is repulsive forces, and there is a increase in the radius we will see. And now question arises, why there is a very less gap between the 4D element and the 5D element. You can remember in the 5D element there is a intervention of the 4f electron, because 4f orbital will be first fielded, after this 5D orbital will be fielded, and 4f electron has a very weak shielding effect. So the outside cell will face the higher nuclear charges, and that is why it will be contracted. And this is called, another effect we called, this is called lanthanoid contraction. The third thing that we discussed, the lanthanoid contraction. And this impact, lanthanoid contraction, due to this, there is a very little gap in the radius of the 4D and the 5D elements. So we understand the atomic radius. Now we are going to discuss the atomic, that is ionic radius. In the ionic radius, what we find, higher charges on the ions, higher charges in ion means it has less radius. The radius or diameter will be, atomic radius will be less. And we go across the series, what we find, that atomic radius is going to be decreases, as just like for the neutral atom we see. For the ion also it will have the same effect. And with the decreasing, as we go down the groove, we will also find there is a increasing of the atomic radius for the ions also. So this is the where the atomic radius or ionic radius, that you can understand. Now we are going to discuss another thing, that is the metallic character. More metallic than any other representative element. Why it is so? This is because of the fact of the presence of the metallic bonding, that we know in the chemical bonding chapter about the metallic bonding. What is that metallic bonding? Metallic bonding is basically, this bonding is created by the free electrons. When there is the number of free electrons, that is the unpaired free electron, that we have to always remember, metallic bonding, that due to the unpaired free electrons. And we know in case of transition metal elements, there is more number of free electrons, that is 1 or 2 electrons you can find that from the ns orbitals, and more number of electrons you can find, from n minus 1 d electrons. Okay. So what is there? It is unpaired free electrons. There is a strong metallic bonding in the transition element, and that is why it is more metallic as compared to the other representative elements in the periodic table. And as we go from the series, we will find at the middle of the series the element that is the chromium, that is molybdenum or tungsten. It is very hard metallic property, very hard metals we could say. And at the end you see that is a zinc, cadmium of Ag. They are weak metals. Why it is so? Why they are weak metal? Because in the zinc also you will find there is no unpaired electrons. In the zinc, the electronic configuration of the zinc is that you can understand, that is 3d10 4s2. So there is no unpaired electrons. So unpaired electrons is very much essential for making the metallic bonding effective, strong metallic bonding. Here you will find it is a weak metallic bonding. That is the why the zinc metal you will find it is there very weak, whereas the chromium or tungsten, they are very much hard metal. So this is the metallic property of the transition element, and that is due to the metallic bonding, and metallic bonding is due to unpaired electrons. The more number of unpaired electrons that is available for the transition elements. Because of the n-9 d subcell, you will get some electrons. Ns, you can get some electrons. So more number of electrons means that is a strong metallic bond. Okay. Now the C point that we are going to discuss, it is again a very important point, that is the melting point. Melting point and boiling point. Melting point and boiling point, again a very important characteristics of the transition metal elements, because it is having very high melting point and boiling points. And when we go across the series, what we find, this is also a very interesting trend, as we have observed in case of radius also. At the middle of the series you will find the elements having the higher melting point, and it goes on decreasing as the atomic number is increasing. That we can easily understand from this graph also. Here we are putting the melting point, and this is x-axis, that is atomic number is increasing. So we will plot all the three series. We will start from the titanium in the first series. Titanium, suppose here the melting point will in this point, then this vanadium, then if this is chromium, and there is a abnormal stage in case of this is titanium, vanadium, chromium, manganese, then Fe, iron, then cobalt, then nickel, and then copper. Copper you will find there is a. This is the 3D series, and this series, let us understand that as we go across the series, what we find at the middle of the series, the chromium, there is an increase of the melting point, and this is due to this fact. Here you will find the maximum number of unpaired electrons. Unpaired electrons, that is, you know that electronic configuration is, what is electronic configuration? That is 3d5 ms. 3d5 4s1. So there is a maximum number of unpaired electrons, and you can see from already discussed, there is a more strong metallic bonding. Metal will be attached to itself in the very strong force, that is called the metallic bonding. So you will find the melting point is very high. After that you will find there is a decreasing trend, and here the copper is, you will find there is decreasing trend. This is a 3D series. Then 4D series, we are solving zirconium. This is zirconium. Then niobium. Then that is molybdenum. Here also you can see molybdenum having the very high melting point, and there is again, like magnesium, you will find there is a abnormal melting point, and here also in the technetium you will find this same trend, and afterwards there is this graph follow this trend. Technetium, then ruthenium, then ruthenium, and then you will find this palladium, and you will find that is your this is Ag. Now this is the 4D series. This is the 4D series, and last we are doing the 5D series. 5D series is like this. This is the first element, that is hafnium. First element is basically tantalum, that is lanthanum, that we are not taking. That now this is hafnium. Then we have the tantalum, then the tungsten, TW, then iridium, and then osmium, then iridium, platinum, and you will find that is a E. So what we find here, that is the 5D series and the 4D series also, as the atomic number, as we go down the group, there is a increase of the melting point, and that is due to this fact that there is a more intensive metallic bonding. You will find this melting point of the tungsten it is 6086 Kelvin. This is a very high melting point, whereas in case of Ag it is having only 234 Kelvin. So this Ag, that is mercury, as the room temperature, is liquid. Why it is so? Because there is a poor metal with intermetal bondings. So we understand the melting points, that as we go across the series, or we can say that atomic number is increasing, so there is a increasing of the melting point up to a middle of the series, because there is a more number of, you can say that is a more numbers of unpaired electrons, and the metallic bonding is very high. After that you will find in case of 3D series, there is in the magnesium, and 4D series in technetium, that is a very abnormal melting point we have observed. Now we are going to discuss another dew point, that is enthalpy of atomization. Enthalpy of atomization. reduction. And this is represented by and this enthalpy of atomization we will find the same trend as we observe in case of melting point, that as we go across the series we will find it is increasing and it will have a maximum in the middle of the series, and after that you will find that it is a decreasing trend. Again, due to this fact there is a metallic bonding is going to influence this observation. So enthalpy of atomization will follow the same trend as we observe in case of the melting point also. And as we go down the groove, we will find that enthalpy of atomization goes on increasing. That is why this transition element is low volatile and it is a very, very hard metal. So that is all for today's lecture. In this lecture that we have discussed the 4 very important physical property of the transition element. That is, first we have discussed about the atomic radius and ionic radius. Then we have discussed the melting point and boiling point, and also discussed the metallic property, and lastly we have discussed the enthalpy of atomization. And this enthalpy of atomization, you will understand that is a very, very important parameter of the elements, transition element, that we will discuss later on, that it will going to help us to understand the electropotential of this transition element. It's a very, very important property that we are going to discuss in the next lecture, that it is having a very good reducing property. So that is all for today's lecture. In this lecture what we have discussed, most probably that is been known to, that has been understandable to you, understand. You most probably you understand it. So thank you very much for watching, and we will visit in the next lecture.